So in this presentation, I will be introducing CUDA, a parallel computing platform and a programming model. The CUDA stands for Compute Unified Device Architecture. It is developed by NVIDIA and helps developers speed up their applications by allowing them to write code that can be executed on multiple GPU cores simultaneously. CUDA is often mistakenly thought of as a programming language or merely an API. In reality, it's a full-fledged parallel computing platform. At its core, CUDA provides both a low-level driver API and a high-level runtime API. Structurally, the CUDA platform is layered. At the top, apps and frameworks like PyTorch and TensorFlow leverage CUDA for deep learning, while CAD software and simulation tools also integrate with CUDA for advanced graphics. Hi, so today in this presentation, I will be introducing CUDA, a parallel programming platform and a parallel programming model. So what is CUDA? CUDA stands for Compute Unified Device Architecture. It is developed by NVIDIA and helps developers speed up their applications by allowing them to write code that can be executed on multiple GPU cores simultaneously. CUDA is often mistakenly thought of as a programming language or merely an API. In reality, it's a full-fledged parallel computing platform. At its core, CUDA provides both a low-level driver API and a high-level runtime API. Structurally, the CUDA platform is layered. At the top, apps and frameworks like PyTorch and TensorFlow leverage CUDA for deep learning, while CAD software and simulation tools also integrate with CUDA for advanced graphics and scientific computing. CUDA-X libraries serve as HP modules for tasks in machine learning, deep learning, HPC, and more. These libraries are designed as middleware, simplifying development by shielding the underlying CUDA APIs. CUDA Toolkit provides a compiler, developer tools, debuggers, and profilers needed to write and debug GPU kernels. Finally, the CUDA driver manages the interaction between the GPU and the OS. This layered architecture ensured that developers can build powerful GPU-accelerated applications while taking advantage of the latest GPU hardware innovations like NVIDIA's Ampere architecture. CUDA is also a programming model, provides extensions to many languages, including C++. CUDA has a keyword called kernels, representing a special function that executes in parallel across many GPU threads, rather than just one, like standard C++ functions. Kernels are declared with a global specifier and launched using the angle brackets, which specifies how many parallel threads should execute the kernel. For example, consider a kernel function called vec_add that takes two vectors A and B and add them element-wise to produce vector C. In this kernel, each GPU thread calculates one element of the output vector identified by the building variable thread_idx.x. The host code then calls this kernel with ingress to compute all elements in parallel. The CUDA program has two parts. The CPU part is host code and the GPU part device code. The CPU part is stored in the host memory and runs on the CPU, responsible for launching kernels. The GPU part is stored in the device memory and runs on the GPU in parallel. CUDA kernels allow developers to execute functions on the GPU called from the CPU, enabling HPC. CUDA-capable GPU serves as the overall hardware platform composed of multiple streaming multiprocessor. Each SM is responsible for executing several thread blocks, which are groups of threads that share local shared memory and can collaborate efficiently. All the blocks launched in a single kernel form a grid, and these blocks can be distributed across different SMs to execute in parallel. CUDA thread hierarchy and 3D index allow programmers to use angle brackets syntax defines the size of grid dim and block dim. The built-in variables thread IDX, block IDX, and block dim can be used directly in the kernel function to uniquely identify each thread and its position in the grid. This mechanism supports 1D, 2D, and 3D grid and block structures, which is very suitable for efficiently parallel processing of multi-dimension tasks, such as vector, matrix, and body data. For example, in the code, back_add demonstrates a 1D index, an element in each thread processing vector. mat_add demonstrates a 2D index, an element in each thread processing matrix. CUDA uses these beauty indexes to naturally map multidimensional data into GPU threads. This figure shows the memory hierarchy of CUDA. Each thread has its own register and local memory. Each thread block has shared memory. Clusters formed by multiple thread blocks share distributed shared memory, and all thread blocks share global memory, such as a hierarchy helps to efficiently organize and access memory and improve the performance of GPU parallel computing. The CUDA threads access data from multiple memory spaces to optimize performance. Local memory for thread-specific data like local variables, shared memory for fast intra-block communication, for example, storing intermediate results of matrix multiplication within a block. Global memory for sharing large data structures like neural network weights across all threads. Constant memory for read-only frequently accessed data such as filter parameters and convolution. And texture memory for read-only cached data optimized for 2D and 3D sampling, for example, images. Distributed shared memory allows threads in a cluster to read and write each other's data shared memory with atomic operations. And global, constant, and texture memory persist across kernel launches. CUDA's thread block clusters enable threads from multiple thread blocks up to 8 to cooperate and communicate beyond their usual shared memory scope, leveraging distributed shared memory across blocks in the same cluster. This is useful for large-scale computations like histograms or reductions. Clusters are defined at kernel compile time using cluster dim's XYZ attribute or launched dynamically using CUDA launch kernel X. This example shows a cluster kernel with 2 blocks in X, 1 in Y and Z, launched by first setting thread block dimensions, for example, 16 times 6 threads per block, calculating the number of blocks, and launching the kernel. It highlights the grid dimensions must be a multiple of cluster size, enabling communications and optimized performance for complex GPU tasks. CUDA has a special function called sync threads to let all threads within the CUDA block synchronize at specific points to safely share data in shared memory. All threads must reach the same sync threads line. Early threads will wait for everyone to let them arrive before proceeding. This approach is crucial when loading data into shared memory, for example, tiles of matrix data, performing computations, and then synchronizing again before moving to the next iteration. CUDA's heterogeneous programming separates CPU RAM and GPU RAM, so they cannot directly access each other's data. The traditional approach, CUDA malloc on the left, explicitly allocates memory on GPU and using CUDA memcopy to manually transfer data, as shown in the code where it copies data back from the device to host. In contrast, unified memory, CUDA malloc manage on the right, allows CPU and GPU to automatically share the same pointer, avoiding manual copying, but with potential performance trade-offs. In CUDA, ASIC SIMT allows memory transmission and computing tasks at the same time. For example, the CUDA memcopy async command cannot block data transmission when the kernel is executed. There are also synchronization tools such as CUDA barrier and CUDA pipeline. These tools can flexibly control synchronization of different levels, such as letting only the current thread wait or letting the same thread block the whole device and even the CPU wait. So those approaches are all avoiding data conflicts when multitasking is running at the same time. In CUDA, the single instruction multiple threads programming model defines GPU scheduling in warp units, and each warp contains 32 threads. These 32 threads execute the same instruction at the same time, but each thread has its own register and programming counter. When encountering a branch, such as if-else, the thread may diverge to execute different paths, forcing some threads in the same warp to stop and wait, causing serialization, which reduces execution efficiency of the entire warp. Even if the number of threads declared in the kernel is less than 32, the GPU will still assign a complete warp. The idle threads are still assigned but do nothing at all. This is done to make the parallel execution hardware design of GPU more efficient. In CUDA's coalescing programming model, if the global memory address accessed by a warp 32 threads is contiguous, the GPU will combine them into a memory transaction, thus reducing the number of memory transactions. This can improve the memory bandwidth utilization rate, reduce global memory latency. On the contrary, if the access address is random, there will be multiple memory transactions and performance will decline. Next, we'll take a deep dive into a classic algorithm, matrix multiplication. We'll first run a baseline performance test using the most basic naive kernel, mat-mul naive kernel, and then gradually try various optimization strategies. So this mat-mul naive kernel function runs on the GPU. The global modifier indicates that it's a kernel. It uses CUDA building variables, block IDX, block dim, and thread IDX to calculate the matrix row and column that the current thread is responsible for. Row and column are calculated using block index and thread index, indicating which position in the C matrix the current thread will update. Then there's a for loop that performs the dot product for a row from matrix A and a column from matrix B, storing the final result in matrix C. Although this is a basic version without shared memory optimization, it demonstrates that the core idea of GPU parallel computing, each thread computes one output element of the matrix, maximizing parallelism and fully leveraging a GPU's power. Next, let's build on the fully naive matrix multiplication kernel. The mat-mul coalesce kernel leverages built-in variables to calculate each thread's unique 2D matrix coordinates from its 1D thread index using thread idx.x divided by tile size and thread idx.x modulus by tile size. So this 2D mapping ensures that each thread computes a single output element of matrix C in parallel and enabled coalesced memory access when reading from matrix B, generally improving memory bandwidth utilization. However, this naive implementation does not use shared memory, causing redundant global memory accesses, and it assumes that a fixed file size that might not fully utilize the GPU's parallel resources if not carefully tuned to the hardware. The mat-mul shared memory kernel divides the output matrix into tiles, which is tile size times tile size, with each thread block computing one tile independently to leverage grid-level parallelism and run across multiple SMs in parallel. Within each block, threads can cooperate to load tiles of A and B into shared memory, reducing costly global memory reads. Each thread computes one partial sum of the output tile using the loaded tiles. And the sync threads function is used to synchronize threads after loading data and after computing each tile's contribution. The shared memory strategy reduces data and reducing global memory bandwidth usage compared to the naive approach. So this run kernel function sets up and launches a CUDA kernel for matrix multiplication. This process actually starts on the CPU by allocating GPU memory from matrix A, B, C using CUDA malloc, and then copies B from the CPU to the GPU with CUDA memcopy. This kernel is launched with the grid and the block configuration using kernel grid dim, block dim, where each block has multiple threads. After sync execution, CUDA device synchronize function ensures all GPU computations are complete, and the results, which is C matrix, are copied back to the CPU with CUDA memcopy. Finally, CUDA free function avoids memory leaks. The main function compares different matrix multiplication strategies and initializes matrix A and B and C on CPU, measures CPU matrix multiplication time, and then launches 3 different GPU kernels, naive, coalesced, and the shared memory using run kernel. The execution time of the CPU-based function and all 3 kernels are measured. The output shows that execution time of matrix multiplication on an NVIDIA Tesla T4 GPU, a popular data center GPU designed for AI acceleration and HPC. The results shows that CUDA kernels significantly improve performance over CPU-based computation. The CPU one takes over 8 seconds, while the shared memory one runs in just 4.42 milliseconds. So the shared memory kernel has the best performance, followed by the coalesced and then the naive kernels. So this is all my presentation. Thank you for listening.